Good day, Doctor. My name is Tang Hui, and my metric number is 299390. Let me start with the part of introduction in this presentation. Multivariable calculus extends single variable calculus to functions like f of x, y, and z. Where x, y, z are independent variables, it helps analyze complex relationships and phenomena involving the multiple quantities simultaneously, essentials in physics, engineering, and economics. It enhances our understanding of real-world dynamics through gradients, optimizations, and integral across the multiple dimensions. For the differential calculus of several variables, this involves studying rates of change of slopes of curves in multidimensional spaces. It extends the concept of derivative to functions with multiple independent variables, essential for understanding how small change in one variable affect others. For the integral calculus of several variables, it addresses the accumulation of quantities over multidimensional regions. It generalized the single variable integration to higher dimensions, crucial for calculating volumes, masses, and other complex quantities in physics, engineering, and also the economics. For the importance of multivariable calculus, it is for the enhanced understanding of complex systems. The multivariable calculus provides a deeper insight into the complex systems by allowing us to analyze how multiple variables interact and influence each other. This is crucial in fields such as physics, engineering, economics, and biology, where systems are inherently multidimensional. Also, it allows us to have the multidimensional analysis. It extends the single variable calculus to functions with multiple variables, enabling us to study phenomena in higher dimensions. This capability allows for more comprehensive analysis for the spatial relationships, rate of change across the multiple parameters, and the behavior of dynamic systems. For the applications, it includes many. For example, from modeling physical phenomena like fluid flow and electromagnetic fields to optimizing the financial portfolios and understanding the biological processes. The multivariable calculus plays a pivotal role in modern science and technology. Now is the application of differential and integral calculus of functions of several variables in the various field. The multivariable calculus can be used for calculate revenue and profit maximization. The first one is pricing strategies. In business, calculus helps determine the optimal price to maximize the revenue. By modeling demand as a function of price and differentiating, we can pinpoint the price point that maximizes the revenue. The next one is profit optimization. Businesses use the multivariable calculus to optimize profits by analyzing how different inputs like labor and capital, which can affect the profitability. This involves differentiating the profit function with respect to multiple variables to find the optimal combination of inputs. The multivariable calculus also allows us to do the marketing analysis and the forecasting. With consumer behavior modeling, calculus plays a key role in analyzing consumer behavior by examining how change in factors like price and income impact demand. Partial derivatives help quantify the sensitivity of demand to these variables. For the forecasting sales and trends, integral calculus is essential for forecasting future sales and trends by integrating data over time, such as sales figures, advertising spend, and economic indicators. We can predict future market conditions and plan accordingly.
Hello, madam. My name is Wong Junho, and my phone number is 298182. And today I would like to present about the integration of calculus. So, what is multiple integration? Integral is one of the fundamental operation calculus. It's a continuous analog or sum. It allows the calculation of quantity that vary over a region in space. And it has two key concepts. One is double integral and one is triple integral. And double integral has two parts. One is double integral over a rectangle, and one is over a region. And the difference we'll discuss later. And normally, the double integral used in to find the area, surface mass, and any other two-dimension of property. The triple integral normally used to find the volume, solid mass, and other three-dimension property. Now I'll continue to present about the differences. The first is the differences between the two types of double integral. The first is the double integral over the rectangle. The difference is the limit is constant. For example, the xy is in the certain limit range. But the double integral over the general region, the limit is not constant. For example, the y is limited by a function, and the function gx and gx2 will change depend on the x. And the difference between the double and triple integral is double integral normally used to calculate the volume under a surface above the XY plane, but triple integral normally used to calculate the volume in 4 space under a hypersurface. In other words, the triple integral normally used to measure the volume under 4D. And next, I will talk about the Fubinian theorem and Stonering theorem. Actually, these two theorems is trying to proving the same equation, which is the order integral can be switched if you fulfill a certain requirement. For the Fubinian theorem states that if the function is continuous on a rectangle R, the order of integral can be switched, but must be make sure that is the R is given in specific number, mean that the limit cannot be infinite, but can be negative. And for the tunneling theorem is different. Tunneling theorem normally apply on the non-negative function, mean that the variable can be infinite, but cannot be negative. So when the equation fulfill these two requirements, it also can be switched for the order of integration. Last, I would like to share about the application of multiple integral, and I think you will become more clear about the difference between the double integral and triple integral after you see the application. First, we look at the double integral question first. The question asks us to find the mass with the variable density. The calculation is very simple, just integrate the density function by the area. And after integrate, you'll get answer. But the point must be mentioned that is the mass you find that is the mass of lamina. You can understand that is the mass of a plane or mass of the surface. That's also why I just now I mentioned that double integral normally used to find the two-dimensional property. And we're going to triple integral. We're trying to find the mass with the variable density. Almost same process, also integrate the density function, but using the volume mean that we integral try. But the difference is the final answer, the mass you get is the solid mass. Mean that you get the mass is the whole solid mass, not just a plane mass. So I think that this can help become more understand between the double integral and triple integral. Thank you.
Hi Miss, I'm Yanzi. Today I'm gonna to present about differential calculus of functions of several variables. What is partial derivatives? Sometimes the function depends on two or more variables, so derivative converts into the partial derivative since the function depends on several variables. Partial derivatives is used in vector calculus and differential geometry. There is two key concepts of partial derivative. The first is simple derivatives. It used to find tangent plane linear approximation, maximum or minimum values, and so on. Second is higher order partial derivatives. Example is second derivative test to determine local maximum, local minimum, or saddle point. Definition of partial derivatives. If function f with variable x, y is a function where f partially depends on x and y, and if we differentiate f with respect to x and y, then the derivatives are called the partial derivative of f. The formula for partial derivative of f with respect to x taking y as a constant is given below. And here also show the partial derivative of function f with respect to y keeping x as constant.
Now I'm showing you one of the application of partial derivative, which is marginal productivity. Question above is to find the marginal productivity of labor and the marginal productivity of capital. The first step is to find the fx and fy. After that, we know the value of x is equal to 100 and value of y is equal to 30, and we substitute into both equation for fx and fy, and we will get the marginal productivity of labor is equal to 13 units, and marginal productivity of capital is equal to 22 units.
Theories and laws. There is a Clairaut's theorem for higher order partial derivative. Clairaut's theorem tells us that if fxy and fyx are both defined and continuous in a region containing the point AB, then fxy is equal to fyx. Let's see the example 1. Let's function f with variable xy equal to 3x squared minus 4y cubed minus 7x squared y cubed. Previously, we determined that fx equal to 6x minus 14xy cubed and fy equal to negative 12y 12y squared minus 21x squared y squared. We have four second derivatives, but as Clairaut's theorem tells us fxy and fyx, so we really only need to compute three of them. Solution 1 show you all four to illustrate the theorem, but you focus on the fxy and fyx. Actually, the answer is same. That is negative 42 xy squared. So the Clairaut theorem are proven. Okay, that's all for me. Thank you.
As a conclusion, the differential calculus in multivariable functions focuses on understanding the rates of change, gradients, and optimizing functions in multidimensional spaces. It allows us to explore how functions vary with respect to multiple variables simultaneously. The integral calculus extends into multiple dimensions, where it integrates over regions in space to compute volumes, masses, and other physical quantities. This integration is essential for calculating cumulative effects and aggregating data across multidimensional domains. These concepts are fundamental for understanding complex systems where interactions between multiple variables are at play. They provide powerful tools for modeling real-world phenomena, optimizing processes, and making informed decisions across various disciplines. Here's the encouragement for further exploration. Consider delving into vector calculus and differential equations with multiple variables. These topics enhance your analytical capabilities and provide deeper insights into the complex systems. These concepts are allowed to act as applications in modern fields, investigate how these concepts are applied in machine learning and data science. Understanding multivariable calculus can significantly improve modeling and optimization in these cutting-edge fields. Engaging with these advanced topics and applications will not only deepen your mathematical knowledge, but also prepare you for innovative work in various scientific and technological domains.